2025 A-Level Combined Mathematics Paper 2 Part A question number 3. This question says two particles P and Q of masses 4m and m respectively are connected by a light inextensible string. The string passes over a small smooth pulley A fixed at the top of two fixed planes, each inclined at an angle of pi by 4 to the horizontal as shown in the figure. So if we look at the figure, we can see we have this plane and this plane which are fixed, which means they don't move no matter what force you apply, which are both inclined at pi by 4 radians to the horizontal. At the top of them, when they intersect, we can see we have a small pulley A which connects two particles P and Q using a slight inextensible string. Now considering the question says the plane on which particle P is placed is smooth, meaning that there is no friction, and the plane on which the particle Q is placed is rough, meaning that there is some friction on that plane. The coefficient of friction between Q and the rough plane is equal to half, meaning that if you consider the force applied by Q in the direction that is perpendicular to the plane, then that force multiplied by the coefficient of friction, which is half, is equal to the frictional force when we reach limiting friction or dynamic friction. Now in this case, since they just say coefficient of friction, we have to assume that dynamic friction and limiting friction are the same value, and for both of them the coefficient of dynamic friction and coefficient of limiting friction are both equal to half. It then says the particles are held with the string taut and the parts AP and AQ of the string lying along the lines of greater slope of the respective planes, meaning that this line AP is parallel to this plane. Similarly, this line AQ is parallel to this plane. So the reason that this is important is because it means that if we consider the forces here, all forces can be divided into forces that are perpendicular to the plane and forces that are parallel to the plane. At the end of the question, it says the particles are released from rest, and it is given that P moves down the plane. Now this is important because of course P could also not move down the plane. Because there's a friction here, it might be possible for the particle P to simply not have enough force to pull the particle Q up. But in this case, it's given that it does in fact happen. The two particles do move, Q moves up and P moves down. Finally, it says obtain equations sufficient to determine the tension of the string. Now this one line makes this question extremely easy. If you consider the entire question, it looks quite big, which might make you think the question is difficult. But this one line, obtain equations sufficient to determine the tension of the string and not solve for the tension of the string, makes this question very easy, because all you need to do here according to this instruction is simply create a bunch of simultaneous equations that you can substitute and solve and simplify down to get tension equals and some variables in the right side that we do know. So all we need to do is to obtain the equations. We don't need to solve them or anything. We just need to obtain a bunch of simultaneous equations that we could potentially use to cancel out a bunch of variables, simplify down to get tension equals an expression of the bunch of variables that we do know. So if we consider what we have here, we have a bunch of forces applied or in this system right here that we haven't drawn. There's a downward gravitational force here, there's a downward gravitational force here, there's an acceleration downward, an acceleration upward, there's also a tension here which we're not considering, there's also a normal force here, a normal force here, and so on and so forth. So what we would be expected to do in this kind of question is to label every single force and then using resolving, construct a bunch of simultaneous equations that we can use to solve this problem. So when doing this, you could either draw all of those forces in this diagram right here, or what I prefer to do, not draw on this diagram and instead draw my own diagram, mark all of the forces and then construct simple simultaneous equations that we could use in order to find the tension T. So if I just mark out the diagram, this is going to be identical to what we have up there, except I'm going to add all the forces additionally. So if we just draw, we have a particle on this slope which has a string connected going up like this. On the other side also we have a particle connected with the same string. At the top we have a pulley which I don't really need to mark, but I'll mark it. On this side, the particle P has a mass of 4m, so I'm going to start marking forces with a downward gravitational force of 4mg. Now since this particle is on this surface here, on this plane, there is going to be a normal force since the particle is not falling through that plane, and therefore if I draw that, it's going to be a normal force like this. Now I'm going to temporarily label this normal force as R for normal reaction. Now additional to these two forces, in the string there's also going to be a tension force which I'm going to label as capital T like this. Since this entire string is inextensible and the pulley is frictionless, this same tension force is going to be experienced by the pulley here, And also on the other side, when we have the particle Q, Q is going to experience that same tension force up the slope like this. Now since particle Q also weighs a certain mass, it weighs mass m, it is going to have a downward force on it, downward force of mg. And as for the fact that it's on this slope, it's also going to have another normal reaction which I'm going to label in this direction. Since the last normal reaction had symbol R, I'm going to label this one with S. Now additionally to this, since this particle is sliding down and this particle is sliding up, we are also going to have some accelerations here. There's going to be acceleration here, which I'm going to label with double arrows, and I'm going to label it F. And up the slope also on this side, this particle Q is going to have upward acceleration, and since the string is inextensible, it is also going to be equal to F. However down this thing goes, this is also going to go up by the same distance. So however fast this thing accelerates downward, particle Q is also going to accelerate upward at the same speed. So I'm going to label the particles. I'll label this particle P, I'll label this particle Q, and additional to these forces, remember that this surface here has friction, which means that if we consider frictional force, there's also going to be a downward frictional force like this, called, let's say, F in this direction. Now remember, the frictional force is always going to oppose the motion. In this case, if the acceleration is up the slope, then the frictional force is going to be down the slope. Now considering all of this, all we have to do in order to find the tension T is to construct a bunch of simultaneous equations that contain T and other variables that we can simplify down to obtain T equals something. Now in this case, if we start making equations with these variables, one thing that we can do is to apply F equals ma. So vector F equals m vector a. If we consider applying F equals ma, we can apply it in different directions. But since all of the forces are either in this direction or perpendicular to that direction, or in this direction or perpendicular to that direction, what we could do is apply our F equals ma down the slope and perpendicular to the slope, and up the slope and perpendicular to the slope. Now if we consider doing that, if we consider, let's say, for particle P, if we apply F equals ma down the slope like this and consider the forces involved, we have an R force which is perpendicular to that, so it's not going to contribute. We have a T force that is in the direction but is in the negative direction, so we have negative T. And then additional to that, we also have mg force, but the mg force is not in the direction that we're considering. We're considering this direction, but the mg force is straight down. So in order to do this, we need to take the component of this force that is acting down the slope. Now in this case, as we can see, this angle is pi by 4, which means that the component that we're considering that's going down the slope is the sine component. So if you consider that it's in the positive direction, it's going to be down the slope. So therefore we have plus 4mg times the sine of pi by 4. Now this is going to be equal to ma. So this is the total forces in the downward direction. It has to be equal to ma. In this case, the mass is 4m and the acceleration a is f in the downward direction or the positive direction. So therefore we have mf. This is equation number 1. You can see this equation contains T, which we want to find. It contains 4mg, where m is a known variable and g is a known variable, and of course the sine of an angle is a known variable. But it also contains this value here, f, which is unknown. Now in order to find f, we need to construct more simultaneous equations. So now that we've done down the slope, you might be tempted to try perpendicular to the slope for particle P. But if we consider what's going to happen, we're going to have R that's perpendicular to that direction, and we're also going to have a component of mg down. Now R is not relevant to our question since we want to find actually T, and R and T are not going to have any special connection since the surface here is frictionless. So we don't need to find it, so we can actually skip that. Now we've done down the slope for P. We didn't do perpendicular slope for P because that would be not useful. But now if we move to Q, we can do Q perpendicular to the slope and also Q parallel to the slope. So if we consider Q, for particle Q, we can go parallel to the slope, and for particle Q, we can go perpendicular to the slope. Now considering Q parallel to the slope, in the upward direction which I'm taking as positive, this direction is positive, we have a force T. So we can write T. And then additional to that, we can see we have two more forces, but both of these forces, F and mg's component in this direction, are actually in the negative direction. So we have minus F and minus mg's component in the downward direction. So once again, since this angle is also pi by 4, the component we have is the sine component. So this is mg sine pi by 4. Now that is all of the forces that are acting in the direction that is parallel to the slope for particle q. If we consider the mass of particle q and the acceleration, this is going to be equal to, the mass of particle q is m and the acceleration in the upward direction is f. So mf. Now here we can see we have another set of variables that we have here. We have an unknown variable and another unknown variable f that we need to find. But additionally we have a known variable that we need to solve for later, and additionally we have also t. These two variables, of course, m and g, are known. Finally, if we consider the direction that is going to be perpendicular to the slope, we have a force s, and we also have the mg component that is in this direction. Now in this case it's of course going to be the cosine component. So if we consider in this direction being positive, we have s minus mg cosine of pi by 4. And if we consider the acceleration in that direction, since the particle q is not going upward or downward relative to the slope, it is equal to 0. This is equal to 0. So we can see this will directly get us the value of s in terms of mg and of course cosine of pi by 4. Now this is equation number 3. Now in addition to these 3 equations, there's one more equation that we need to write down, and that equation does not have to do with F equals ma, but is rather the relationship of this frictional force F and this normal force S. So as we know, since the particle here is moving, what we have is dynamic friction, which means that if we consider the equation, dynamic friction F sub d is equal to mu sub d times r, where mu sub d is the coefficient of dynamic friction and r is the normal force. So this is the theory that we know. Applying it to this particular situation, the frictional force F sub d in this case is just F. So we have F is equal to, and mu sub d here is the coefficient of dynamic friction, but in the question we are just given the coefficient of friction. So you have to assume here that the coefficient of limiting friction and the coefficient of dynamic friction are both equal, and they are both equal to a half. So if we substitute assuming that, we get a half here, and then the normal reaction here is S. So F, the frictional force, is equal to half S. And this is going to be equation, let's say, A. So using these 4 equations, this equation and these 3 equations obtained from F equals ma, we can see if we substitute this equation, we can get rid of S and replace it with instead F, or we can get rid of F and replace it with instead S. If we then use these 2 equations, we can get rid of F completely and have only 2 equations which have T, M, G and F, and T, Mg and F, which if we combine, we are going to be able to get rid of either F or T. Since we want T, we're going to have to get rid of F, and if we get rid of F, we're going to finally have an equation of T where T is given by only known variables. So this of course is the goal here. We need to obtain equations sufficient to determine the tension of the string, which means that once we obtain these equations, we are actually done. So this is actually the end of the question. This is all we need to write. Now finally, if we consider the marks awarded for this question, for drawing the diagram like this or marking all of the forces, you actually get 5 marks. So for marking all the forces like this, and of course all of the forces need to be correct, they need to be in the correct directions, and they need to be, marked on the correct objects. If you apply all of this and mark all of the forces with the correct magnitudes and all of that correctly, you get 5 marks. Now after this, for the remaining equations, when you use the dynamic friction equation and obtain F equals 1/2 S like this, you get 5 marks. And for each of these 3 F equals ma equations, you get 5 marks, 5 marks and 5 marks. Now of course, in order to obtain these marks, each of these equations need to be done correctly. And in order for each of these equations to be done correctly, you need to apply F equals ma in the correct directions and make sure you don't mess up the signs. In this case, we apply F equals ma downward. Since the T is acting upward, T is going to be negative. Hence why T is negative here. So if you do all of that, you can get a bunch of easy marks with this question, and all you need to do here is to of course remember that you're not expected to solve any of the equations. You're just expected to write down a bunch of simultaneous equations, and then that is it. So here of course the main important points that I have to say is that you need to mark all of the forces. You need to mark all of the forces. You cannot avoid marking all of the forces. Remember all of the forces in your head and just write down the equations. You will lose marks by doing that. So that is going to be the end of this question and the end of this video. So I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching and goodbye.